So let us start the second part of this lesson. We want to talk about Hopital's rules. There are two of them, and these are applications. I mean, this is a very good application of derivatives, so it will help you to calculate some type of limits, more or less all types of limits. Okay, but there are two rules. So let me just emphasize what the rules are. So let us assume that I have a function f and g. Okay, they are differentiable on an open interval, for example, on a and b. Okay, and then we know something. We know that the limit of f of x. So when I say that they are differentiable on an open interval a and b, so let us imagine like this. So here is your a, here is your b. They are carved out because this is open. And then you know that there is at least an interval on which these two functions are differentiable. And you know something. You know that when x approaches to a from the right-hand side within that interval, so how should I write it? I should say that x goes to a from the right-hand side is equal to the limit of g of x, x goes to a plus from the right-hand side. Both of them should be 0. And then for all x in this interval, g prime of x is not equal to 0. And we also know that for some reason this limit exists. The limit of the derivative of f divided by the derivative of g when x goes to a from the right is equal to L. It means it exists. So let me not write this, because even if it is infinity, that is correct. So let me write this again. L can be just, I will write it down. You see, the point is that more or less this is what matters. Okay, so if the limit of f and g when x approaches to a from the right hand side, both of them are 0, and the limit of f prime over g prime is L, you can conclude that the limit of f itself over g itself, x goes to a from the right, is the same L. Okay? So when you write it down, it looks a little bit complicated, but it is very simple. So in principle, if you are supposed to calculate this limit, you don't know what the number is, but it is of the indeterminate form 0 over 0. Okay? Then, instead of calculating this limit, you can differentiate the numerator and differentiate the denominator separately, not differentiating the fraction. That is not the case. You differentiate them separately and calculate this limit instead. If you are lucky and this limit turns out to be L, then you can say that, okay, the original limit is also equal to L. The proof of this is not very easy at all. I mean, it's a bit complicated. You need to use intermediate value theorem in a very wise way. But here I just want to tell you how to use it, okay? And there are two of them. I will give you an example. The example is very simple. But the point is that here, L is a number. L can also be infinity. So if the answer is infinity, you can go back and say that my original limit is also infinity. If it's minus infinity, that's also. So L can also be infinity or negative infinity. And there is no reason that it goes to a plus. So for example, you can replace x to a plus by x to b minus, if you go to b. Or if c is between a and b strictly, if c is between a and b strictly, you can replace this x with x to power, x goes to c. So, I mean, it's very, very generic. So it works even if L is infinity. It also works if I have the left limit or if I have a double-sided limit. But the point is that this is not the other way around. And you have to respect this part. Before actually going to the content of the remark that I have written, let me solve some examples. Might be I will also change the in the future I will change the remark and the example, because the examples are extremely simple. So for example, let me start example 6 part 1. So this limit is given to you. So the limit of x to the power of 3 minus 1 divided by x to the power of 2 plus 5x minus 6, x goes to 1. Of course, this is not a complicated limit. In principle, without even the Hopital's rule, you should be able to actually calculate this. You factorize, because first you put 1 there, you see it becomes 0, and when you put 1 here, it is also 0, so it is indeterminate form of the type 0 over 0. And you know how to do it, because this is one of those cases that you factorize this, you eliminate, and this will be done. But definitely you will see that the Hopital's rule is very simpler here in this case. But you need to know, this is the first Hopital rule. The first Hopital rule tells you that when you have the limit of type 0 over 0, you can use it. So can I use the first Hopital's rule here? Yes, because this limit is indeterminate of which form 0 over 0. So what you need to do, instead of calculating this limit, you calculate a new limit that you yourself set up. How? By differentiating the numerator and the denominators separately. So the derivative of this one is 3x squared. The derivative of this one is 2x plus 5. So instead of calculating the original limit, you set up a new fraction whose numerator is the derivative of the numerator and its denominator is the derivative of the denominator, and calculate this limit. Sometimes this limit is much simpler than the original limit, as you can see in this example. Can I calculate this limit simply? It is not even indeterminate now. If I put 1 there, it becomes 3. If I put 1 there, it becomes 7. Now you see, the limit of this new limit exists and is equal to 7. Then I can go and conclude my original limit is also the same number. So this means that Hopital's rule, Hopital number 1, tells me that the limit of x to the power of 3 minus 1, x squared plus 5x minus 6, x goes to 1 is equal to 3 over 7. So this is how we use the Hopital's rule. This is the probably simplest example. But sometimes, of course, I will hopefully give you some examples. You have to use Hopital's rule several times, yes?
If by any chance you were already given both of them, like the derivative form, and you can visually see that they will be like 0 over 0, should you derivate again, or should you try to like go back?
Yeah, of course. So you don't need to word it in that way, because this might be a little bit complicated. You just check the limit. If the limit is 0 over 0, and then you can differentiate the numerator and denominator separately, you set up a new fraction. Momentarily you forget about the original limit and concentrate on this limit. If this limit exists, whatever it is, you can go back and say that, okay, my original limit according to Hopital's rule number 1 is also the same number. Yes? Yes?
Does this work backwards?
No, the backwards will not work. I will give you the remark later. But let us get used to of it, and then we see that backward usually does not work. So you cannot. So this is the only thing you can do with this. It is extremely important, because I have seen that many students are getting used to this so much because it's very convenient that whenever they find a limit, they just use Hopital's rule. No, the first Hopital rule only works if it is 0 over 0, and it is not going backward. There are some examples that I will show you that this does not exist. The original limit exists. Okay, so I have written it in the notes. I will come back. These questions? Okay, so let us do one more at least. So the limit of square root of 2x plus 1 minus 1 divided by the square root of 3x plus 4. Is it plus 4? Yes, 3x plus 4, and then minus 2, x goes to 0. Okay, of course you can solve this without Hopital's rule, but it is a little bit lengthy. But if you know Hopital's rule and you are good in differentiation, it's faster. So first of all, is it applicable?
Yes.
Yes, because if I put 0, this becomes 0 over 0. So it is indeterminate of the form 0, 0. So it is this, the first Hobbital's rule as I described here is applicable. So in principle, you shouldn't write equal. Some people write equal because there's no guarantee they are equal. So you have to start a new line, and then you say that, okay, I calculate this limit. I set up a new limit. How? Its numerator is the derivative of the numerator. Don't take the derivative of the whole fraction, be careful. So the derivative of the numerator, so what is the answer? So it is 2 square root of 2x plus 1, 2. Yes, do you agree? This is the derivative. I'm using this. Square root of u prime is equal to u prime over 2 square root of u. And I will use the same thing here because the derivative of 1 is 0. The derivative of this one is u prime. I'm giving the role of u to this. So it becomes 3 divided by 2 square root of 3x plus 4. But this one is 0, this one is 0. So I first set up a new limit. And then I ask myself, does this limit exist and what the value is? But this is extremely simple because if I put 0 here, it is not indeterminate anymore. So if I put 0 there, so these 2 and 2 are cancelled, so it becomes 1 in the numerator. If I put 0. And in the denominator, it becomes 3 over 2, but the square root of 4 is also 2, so it becomes 3 over 4. And the answer becomes 4 over 3. So if you don't mind, for simplicity, I call it n. Then it is better to write it Hobbital rule number 1. This implies that L is also the same number. So this is the question mark, yes? This is a good way of writing it. Because I have seen many people in the exam write this is equal to this. There is no guarantee they are still equal. You have to calculate the second one. If it turns out to be a number, then yes, they are equal. Okay? Any questions? But sometimes you have to use the Hobbital's rule more than once. So for example, let me write the next one. L is equal to the limit of x minus 1 squared and then divided by the third root of x squared and then minus 2 the third root of x and then plus 1. So x goes to 1. Okay? So here, if you really don't want to use Hobbital's rule, it might be a little bit more involved. It is also possible, it's not extremely hard. But Hobbital's rule, if works, is sometimes simpler. Is Hobbital rule applicable here? Yes, because if I replace x with 1, the numerator is 0, the denominator is also 0. So it is 0 over 0. So this means that I set up a new limit, and for some reason you will see why. Let me call this new limit m. I will consider this new limit, whose numerator is the derivative of this. So I would say let n be this one. And the derivative of this one, can we do it in our head? So if I want to take the derivative of 1, which is 0, so the third root of x can be written as x to power 1 over 3. So if I differentiate it, it becomes minus 2 over 3, x to the power of minus 2/3. Yes? And then this one is the third root of x squared, so it is x 2/3. If I differentiate it, it becomes 2/3 x to the power of minus 1 over 3. Do you agree with me? Am I right? So I differentiate the numerator, it was simple. I used the chain rule, of course, but x minus 1 prime is 1, so I didn't write it. But then I replaced them with the formulas, the power form, and then I differentiate using the famous formula. So 1 over 3 goes down here, so that's correct. Okay. But you see I am in trouble again. You see that? Now if I replace x with 1, still the numerator is 0. That is not bad, but unfortunately the denominator also becomes 0 again. Because if I replace x with 1, 1 to any power is just 1, I will have 2/3 over 2/3. If you want, you can simplify it a little bit, because for example, I can factor a 2 out, and that 2 cancel that 2, and this 3 will go into the numerator. It doesn't matter, but let us simplify if possible. So I would write it in this form. But still, I couldn't solve the problem yet. Are you okay with the algebra? Is algebra?
Can you just explain how you got the...
This one?
Yes, on the right side.
This one?
Yes, exactly.
So this is the third root of x. The third root of x is written as x to power 1/3.
Okay.
And if I ask you what is the derivative, 1/3 goes down. X to power 1/3 minus 1, which is minus 2/3.
Okay.
But because there was an extra 2 here, so you see a 2 here as well. Yes? And then I factored the 2 out. 2's are cancelled. I multiplied by 3. The 3's are cancelled, but I have a 3 up there. Yes? But I hope that you see that I am still in trouble, because now if I replace x with 1, I have again 0 over 0. So this means that again I would say, hence, let. So this is what I mentioned. Sometimes you have to do Hopital's rule more than once. Okay? But it is, hopefully you can see that this is the last time. Why? Because if I differentiate the numerator, it will be only 3. Even if the denominator is 0, it is not a problem. I will have infinity. So it shows that it is hopeful. Yes, I am hopeful, because the next time it will go. So I would say, hence, let, I don't know, k be equal to the limit. I set up a new limit whose numerator is the derivative of this one, which is simply 3. And the derivative of this one is minus 1 over 3 x to the power of minus 1 over 3 minus 1 is minus 4 over 3. And then plus 2 over 3 x to power minus 5 over 3. X goes to 1. Yes? But you see, I don't have any problems anymore. If I replace x with 1, the numerator is 3, and the denominator is minus 1 over 3 plus 2 over 3, which is 1 over 3, which is 9. Yes? Okay, but then what can I say about my original limit now? Because of this limit 9, because k is 9, so I would say that if you want to really understand it, so when I say k is 9, it gives me what? M is 9. And because now m is 9, it gives me L is 9. Something like this. Is that understandable or not? Is the logic clear?
Yeah.
Okay. So sometimes you have to use it more than once. More or less that's it. Okay, now let me go back to the remark that I actually skipped. The remark is important. So it is extremely important to follow the rules. So for example, I'm just discussing about that remark, okay? The remark is written in the notes, so I don't write all of it. So let us say that if I want to calculate this limit, so let me make it 1 plus here. If you use Hopital's rule here, it is wrong. Because I have seen some people get used to this method because this is so simple and effective. They don't even think, they just use Hopital's rule. If you use Hopital's rule, what happens? This becomes the limit. The derivative of the numerator is 1. The derivative of ln of x is 1 over x. And x goes to 1 plus. And of course, this is so simple. This is the limit of x when x goes to 1 plus, and then people get this 1 and then immediately say that, okay, and then of course L is 1, which is wrong. Why is that? Because I told you, you have to check the type of limit first. So do I need even Hopital's rule here? No, because when I put 1, the numerator is 1, the denominator is 0. It is not 0 over 0, and I don't need Hopital's rule because I know the answer. If the numerator is 1 and the denominator is 0, I have a number divided by 0, which is of which type? Of infinity type. Okay? But now because x goes to 1 from the right hand side, the numerator is positive, ln of a number a little bit larger than 1 becomes 0 but a little bit larger. So this becomes a positive infinitesimal. So it becomes positive infinity. So the correct answer to this limit is infinity, just in a matter of seconds. So you are using the Hopital's rule and you are concluding something wrong. So it is extremely important you respect this condition, both of them. Another thing is that the other way around does not work. So if you calculate this limit and it does not exist, you cannot say anything about your original limit. Okay, so this is the example, I think, if I can reconstruct it from your book. So for example, let us say that I want to calculate this limit. This is a good example constructed in your book, x goes to 0. Okay, is Hopital's rule applicable here?
No.
Yeah, in principle it is.
But the function is undefined.
What?
Oh, no, sorry.
No, it doesn't matter. This is the limit. X goes to 0, it means that it is not exactly equal to 0. But what type of limit is this? The limit of the denominator, the limit of sine. The limit of sine x when x goes to 0. What is the answer? Sine of 0 is 0. That's very simple. But this one is a little bit problematic, but we already discussed about that. Do you remember how should we calculate this?
The sine of 1 over x is a bounded function.
Yeah, bounded function. This is 0, so the limit is 0. So, this is actually respecting this condition. The limit of the numerator is 0, the limit of the denominator is also 0, so in principle I can use Hopital's rule. But when you calculate the Hopital's Hopital's fraction, you will see that the limit does not exist. And then you might say that, okay, because that limit does not exist, let us go back and say that my original limit does not exist. Then I will show you, no, the original limit exists even though the Hopital fraction limit does not exist. Let us do that. So let me calculate the Hopital's fraction 1. Okay, so how should I do that? If I want to use Hopital's rule, then I have to use the derivative of the denominator, which is extremely simple, which is cosine x. X goes to 0, of course. And then I have to take the derivative of the numerator. The derivative of the numerator is a product rule, so it becomes the derivative of x squared is 2x multiplied by sine of 1 over x, plus the other way around, plus the first one x squared multiplied by the derivative of sine 1 over x. The derivative of sine becomes cosine, but because of the chain rule, I have to multiply by the derivative of 1 over x. But the derivative of 1 over x is minus 1 over x squared. Okay, and then let us simplify this a little bit. So this becomes the limit 2x sine 1 over x. This and that are cancelled. I have a negative sign. Oh, sorry, x goes to 0. Okay, so again, the limit of this part is 1, x goes to 0. The limit of this one with the same rule is 0, but this is also a very famous example. We had it before for sine, the same is for cosine. The limit of this part does not exist. So in principle, the whole limit does not exist. Okay? Okay? So you see, the limit of f prime over g prime does not exist. So don't go backward and conclude that, okay, so then the original limit does not exist as well. Because that is not true. The original limit indeed exists. Okay? So this, you cannot conclude that the original limit does not exist. So if you are lucky and the limit of the Hopital fraction exists and whatever it is, you can go backward and conclude your original limit is the same. But if the limit that you set up for the Hopital's rule does not exist, don't go and conclude, okay, so the original limit does not exist. This is one example. You see, this is the setup for the Hopital's rule. This is the limit of Hopital's rule and does not exist, but I want to show you that the original limit indeed exists. Can you calculate the original limit now? So you see that this is the dead end. Hopital's rule does not work. You see, it was 0 over 0, so it motivated me to start using Hopital's rule. Then what happened that I decided not to continue? because the limit that I got does not exist. So even though my starting point was correct, it was 0 over 0, and I started to use Hopital's rule, then I realized that this limit does not exist. So don't go back and say that the original limit does not exist. If this happens, it means that the Hopital's rule again does not work. Then you have to see that if you can solve that in another way or not. But can you do that? So if this is in the exam, this is a scratch paper, you realize that the Hopital's rule does not work, so you have to throw it out and then find another way. So this is why it doesn't make you independent from what you learned before. So you have to know them, but most of the time it works faster if it does. Yes?
So can it work with sine and cosine functions or not at all?
It doesn't matter about which type of function you are working. You have to respect the conditions of the Hopital's rule. But I'm just telling you that. First of all, you have to respect the 0 over 0, okay, in all the cases. So in this case, it was very clear from the beginning that the Hopital's rule does not work because it is not even 0 over 0. But in this case, it is 0 over 0. But then I am unlucky, after doing a lot of calculations, I realized that the limit does not exist for the Hopital rule. So I cannot go backward and say that my original limit. So it means that whatever I did here is just a waste of time. Okay, so I have to throw it out. There's no way for me. Okay, but now this means that if this is given in the exam, you might realize that, okay, I want to use Hopital rule, then you understand this is in trouble, cross it over, and then you have to find another way. So that is why you are not independent from you learn what you learned before. Okay, because sometimes the Hopital rule is not applicable. But so this means that at this point you have to find another way to solve this problem. But do you see how? By the experience you had some seminar problems. I don't think this is very hard for you now. So you have to write it in a way that you can get rid of this indeterminacy because it is 0 over 0 still. So how can I get rid of it? Do you see that?
X over sine x.
X over sine x, very good. So x over sine x, because this is also a theorem, multiplied by another x times sine x, sine 1 over x. Do you agree? This is exactly this one. But why this is beneficial? Because this limit is famous, the limit of the first part. The limit of x over sine x is what? 1. And the limit of the second one, it's also very famous now for you, hopefully. So what is this limit? So you need to write 0 and bounded. So the limit is also 0. So the limit of the first one is 1, the limit of the second one is 0, so the limit of the product is 1 times 0, which is 0. Okay? So I would say that if you wanted to do the Hopital's rule, that was completely a waste of time. But this sometimes happens, yeah? So this is the complete solution. So be careful when you are using the Hopital's rule. Okay. Let us go a little bit forward. There are some more examples you can do, but there is a second version of the Hopital's rule, and that is for the case. So this Hopital rule number 1 was for the case 0 over 0. We have one more Hopital rule, which is the proof is much harder, but this is only for infinity over infinity. Okay, so if you have infinity over infinity, you can also use Hopital's rule, but that is called the second version of the Hopital's rule, and the proof is much harder. So that's why we have to separate. So far, we learned 0 over 0, but everything we learned about 0 over 0 is also the same for infinity over infinity. Is that right? So we have to do this, we can do the same thing. Okay. So, for example, if I want to do example number 7, so you see, it doesn't matter where x is going. What matters is the type of indeterminacy. So in this problem is also the same case. So you see here, it doesn't matter if L is a number or is infinity. Okay? If this one is infinity, you can go back, if this one is infinity, you can conclude that this is also infinity. And it doesn't matter if x goes to any number or x itself goes to infinity. What matters in the first one is your indeterminacies of type 0 over 0. Okay? And the same is true for the second one. It doesn't matter where x goes. What matters is if you have infinity over infinity. So if you have infinity over infinity, you can do the same thing. So let me solve one example for you. So example number 7, it is the limit of ln of x squared, for example, plus 1 divided by e to power 2x, and then x goes to infinity. So assume that this limit is given to you. The first thing you do is to put infinity to see what type of indeterminacy you are facing. So if I put infinity here, ln of infinity is infinity, e to power infinity is infinity, so it's infinity over infinity. And by the way, here I even don't know how can I solve it in any other way except Hopital's rule. Because if I want to solve it in any other way, I have to be creative to find some kind of inequalities so that I can use a squeezing theorem. And finding those inequalities are extremely hard sometimes. Okay, so I just want you to see that this is really, really beneficial. So the second version of Hopital's rule is applicable here. So again, the logic is the same. You just create, so this is your L. You want to know the answer. So for example, you set up M and say that, okay, let M be this. Okay, you don't need to write this. Okay, so here I don't have to, I can do it once. So I can write the limit. I set up a new fraction. What is the fraction? The numerator is the derivative of the numerator, and this one is the derivative of the denominator. The denominator is very simple. The derivative is this one. And the derivative of this one is x squared plus 1, 2x. I am using this formula. Yes? So here I give the role of u to this, u prime over u for the numerator. U prime is 2 times e to power. X goes to infinity. Okay, so what do you think? Is this infinity over infinity, or what type of this limit is this? So if you want, you can do it one more time, but hopefully you already know another rule. So what is this limit, by the way? So by the way, we could answer this quickly. What is this limit? Do you remember I gave you a remark and I proved one of them? So this is an exponential function, this is logarithmic function. In a battle of between exponential function and logarithmic function, which one will win? Exponential. So you expect that this limit is indeed 0, okay? So, but if you don't want, you have to, so this I cancel these two, so it becomes x over x squared plus 1 e to power 2x. So, and of course, it is infinity over infinity. So you have to do it one more time. So let me call this one m. So I would say let, that was correct. And then let k be the limit of the derivative of the numerator is 1. The denominator is a product rule, so it becomes 2x e to power 2x plus 2x squared plus 1 e to power 2x. Okay? But it is, if it is in the exam, it was much simpler to say that this is a power exponential function, logarithmic function, the answer is 0. But even if you don't do that, you use Hopital rules 2 times, you see that this is indeed the case. So what is this limit now? Because the numerator is constant, the denominator is infinity, so this answer is 0. So this gives me this is 0, this gives me this is also 0. Yes? Okay, so there is no time because the next ones are simple, but there are other types of indeterminacy. This is important now. So other forms of indeterminacy are of these forms. So you have 0 times infinity. This is another type of indeterminate form. But again, when I say 0, I mean infinitesimal. This is a little bit lazy to write like that. Because if it's exactly 0, 0 times a large number is indeed 0. When I say 0 times infinity, I mean a negligible, an infinitesimal number by infinity. So we don't know how big is this or how small is that. That is one indeterminate form. Another indeterminate form is 0 to power 0. And what do I mean? It means negligible, infinitesimal to the power of infinitesimal. Okay? And then another one, of course, we already talked about that, infinity minus infinity, we had it before. But there's also one more, and that is 1 to power infinity. Again, This is something you need to know. When I say 1, I don't mean exactly 1. I mean a number close to 1. Okay, so here means close to 1. Because if it is exactly 1, it doesn't matter. When you raise it to any power, even if it is very high, it becomes exactly 1. But if it is very close to 1, then 1 to power infinity is also something. Okay, none of the Hobbital's rule, because we have only 2 versions, none of them is directly suitable for any of these cases. But we can manipulate them in a way that it becomes relevant. Okay, so let me see which order I have given you. Okay, so let me, example 9, let us talk about this first. So this is example 9. I will come back again. So example 9, let me write one question for you. So limit of x goes to 0 from the right hand side, then I have 1 over x minus 1 over sine x. So assume that this is given in the exam and you're supposed to calculate this limit. Again, you have to always check what type of limit you are facing. What type of limit I'm facing? X goes to 0 from the right hand side. So 1 over an infinitesimal, positive infinitesimal becomes infinity minus. If x is a little bit larger than 0, because sine of 0 is exactly 0, but if x is a little bit positive, so I am in the first quadrant, sine of x is close to 0 but positive. So 1 over close to 0 is also infinity, but there is a minus sign here. So then it becomes infinity minus infinity, so I have this type. And none of these Hobbital's rules are directly applicable. I have to do some algebra to change the form of this to another form. So what do you think would be suitable here? Do you see what algebra gives? Because you know that in both Hobbital's rule we have a fraction. One fraction, f over g. But here I have one fraction minus another fraction. If I insist to use one of these Hobbital's rule, I have to have one single fraction to see if it is possible or not. So at least let us make it one fraction. How can I make it one fraction? To take the common denominator. So this becomes x sine x, and then this becomes sine x minus x. X goes to 0 from the right hand side. So these two limits are the same. But this one is what type of limit now? If I put 0, the numerator becomes 0, and the denominator is also 0. So this means that what type is this?
First level.
And this means that the first Hobbital rule is applicable now. Okay, so what I do, I will calculate a new limit. The derivative of the numerator is cosine x minus 1. The derivative of the denominator is what? The product rule. It becomes sine x plus x cosine x. X goes to 0 plus. But again, what type of limit I am facing? Unfortunately, another 0 over 0, because if I put 0, it becomes 0, and then sine of 0 is 0, this is 0. That's again 0 over 0. Still, the Hobbital's rule is applicable. I have to do with one more. Take the derivative of this is minus sine x. Take the derivative of this is cosine x. This is a product rule, so it becomes cosine x plus x sine x. X goes to 0. So if you don't mind, let me simplify this. Do you agree with me? But do I'm in trouble or not? No. Because if I put 0, the numerator is 0, but the denominator is 2. So I have 0 over 2, which is 0. So then I go backward. This is also 0. And then I go backward. This is also 0. But hopefully you understand what I'm doing, yes? In the exam, write it properly. Okay, the other two ones are more tricky. So what do I have if I have these scenarios? Okay, so let us focus on this one now. Okay. So I have written extensive explanations in the notes, so you can read them if you want to know them very carefully. But this is the gesture of what you were supposed to, this is the essence of what you're supposed to do. So for example, let me go to example 8 and try to solve this problem. So again, this limit is given to you. You need to know what type of limit you are facing. You put 1 there. This becomes 0. But what type of 0? Not exact 0, infinitesimal. And you put 1 here. If it is a little bit above 1, this becomes, because you know that if it is a little bit more than 1, this will be a little bit more than pi over 2. But tangent of pi over 2 is infinity. So, but you are in the second quadrant, so it's minus infinity. So if it goes to 1 from the right hand side, you have 0 times minus infinity. If it goes to 1 from the left hand side, it is 0 times infinity. But in any case, you are facing 0 times infinity. When you have 0 times infinity, the trick is this. I mean, this is a little bit a strange way of saying, but if you have 0 times infinity, this is just very intuitive. Can I write it as 1 over 0? Intuitively, yes? Because infinity over 1 over 0 becomes 0 times infinity. But what is 1 over 0? Infinity. So this is the essence of what I'm saying. Every 0 times infinity by this trick can be transformed into infinity over infinity. But sometimes you can do it the other way around. You can imagine that this is 0 over 1 over infinity. But what is 1 over infinity then? 0 over 0. So this is just intuition. Okay? So it means that any 0 times infinity can be rewritten, if you like, as infinity over infinity, which the Hobbital's rule is applicable. Or you can also write it 0 over 0. For example, here what you can write, you will realize that this is of the type 0 times infinity. Intuitively you can use this trick. But you can see it is very reasonable here. Instead of x minus 1 times tangent, do you agree that algebraically I can write this? There is no doubt about it. And I am not in trouble, because when x is close to 1 but not equal to 1, this is a huge number, but that's a number. So that is completely valid here. Is that right? This expression that I have written here is exactly that expression when x is close to 1 but not equal to 1. But now, this has a formula. So what is that? X minus 1 cotangent. And now what happened to you, what is happening here now, if I put 1 again, this limit becomes 0 over 0, because cotangent of pi over 2 is also 0. So that is the way you have to think, to change 0 times infinity, either to this type or that type. For me, this one is easier. If you wanted to do it the other way around, you have to write it as tangent pi over x over 2 divided by 1 over x minus 1. But this one will be infinity over infinity. So again, Hobbital's rule is applicable, so you can use that. But this is better, yes, isn't it? So I now use Hobbital's rule. I differentiate this. This is 1. I differentiate the cotangent. I have the formula in my mind, so it becomes minus pi over 2, 1 over sine squared pi x over 2, and x goes to 1. But everything is simple because sine of pi over 2 is 1, so the answer becomes simply minus 2 over 1. Okay? And there's one more thing that I want to talk about, are these two. The solutions are of the same type. So the trick that I use for both of them are the same. So let us use one of the examples. And this is probably the first time we more or less can cover everything. Okay, so let me, for example, solve this very famous example. Limit of x to power x, x goes to 0 from the right side. So what type of limit is this? It's a 0, so it becomes 0 to power 0. But again, not 0 to power 0. It's a very infinitesimal to power infinitesimal. So that's indeterminate form. So the thing you have to do for these cases, you have to use this formula. E to the power of ln of any box, do you remember, is the box itself. Yes? This is the famous formula. So instead of x to power x, what I would write it as e to power ln of x to power x. So I am not doing anything now. I am just using this formula and rewrite x to the x like that. Do you agree? Mm-hmm. This is your box. E to power ln of box is the box itself, so everything I have done is valid. But my claim is you can lift this limit to the numerator. But before doing that, there is a formula for ln. Do you remember? X goes to the back. So this becomes the limit e to the power of x ln of x. It is completely valid because x is positive. I am not in trouble with ln. This is my limit. Now, my claim is, I have to justify that this limit can jump to the up, to the exponent. Okay, so it becomes e to the power of limit x ln of x, x to the 0 from the limit. Okay? Why this is true? This is true because we had a theorem before. This is the theorem. If I know that the limit of g of x, x goes to a is L, and if I know that the limit, and I know that f is another function is continuous at L, this is a theorem we had before. If I have two functions, the limit of g of x is L, f is continuous at L, then the limit of f of g of x, x goes to a, is equal to f of L. If you see the notes, we're from the first week, I think, you will see this theorem there. Okay, so in other words, the question is that limit, if I want to make it more formal, so the question is that can I flip the limit and pass it from f and move it to g? In other words, can I bring f out and push limit in? The answer is yes under two conditions. The answer of this flipping is yes under two conditions. The first condition is that this limit exists and f in the value of this limit is continuous. If you can do that, you can flip. So here I can do that. Why? If this limit exists, because exponential function is continuous, this part is guaranteed by the continuity of exponential function. So if this limit exists, this flipping is possible. Okay? So this means that if I want to, so this means if this is, so let me write, if the limit of x ln of x, x goes to 0 exists. Okay, so this question mark, I have to answer that. But this limit, what type of limit you are facing now? That's just 1 or 2 minutes. So what is this limit? What type of limit you are facing? What type of limit you are facing? Put 0 there. This is 0. Infinity. So 0 type infinity, it means that you reduce this form to a previous form that you know what to do. So if I want to calculate this limit, okay, what can I do, for example? I can use one of these intuitions. Okay, I prefer to move x to the bottom. Yeah, so it becomes limit ln of x 1 over x. X goes to 0. Algebraically, everything is sound and clear. Yes. But what is the benefit of that? The numerator is infinity. The denominator is also infinity. So this is now of the type infinity over infinity. So then I can use Hôpital's rule. So it becomes, so Hôpital's rule will tell me ln of x prime divided by 1 over x prime. But then what happens, this becomes the limit 1 over x. This one I have it in my memory. And then, so be careful, this is still infinity over infinity, but the algebra is simple. So I just write it like minus x. Because if you simplify this expression, it's just minus x. The answer is 0. So you see what I did? I use this formula to rewrite my limit into this form and use the property of ln to move this backward. And I am using this theorem. The second part is always guaranteed for these problems because exponential functions are always continuous, so don't worry about this part. The only thing that you have to be worried about is that if this limit itself exists or not. So you use the L'Hopital's rule as you learned for the case of 0 times infinity. You calculate it and you find it 0. But be careful, what is the answer to your original limit? I calculated this part to be 0, but my original limit is e to power 0. Okay? So the limit L that I am looking for, is not 0, is e to power 0, which in this case is 1. Is that clear? So these are all types of L'Hopital's rule that are applicable. But please go home and pick up the other ones that I didn't have time to go through them and then do them once to see how it works. This is very simple. So, and I have explained everything in detail in the notes. So if you read it, I think you will be able to understand. Any questions? Thank you very much.